We'll start in about a minute. Today we'll cover how to solve triangles that are not right triangles by using the law of sines in section 10.1, and then in section 10.2, the law of cosines. Okay, so triangles that are not right triangles are called oblique triangles. An oblique triangle will either have three acute angles. An acute angle is an angle whose measure is between 0 degrees and 90 degrees. Or it will have one obtuse angle and two acute angles. An obtuse angle is greater than 90 degrees. For an oblique triangle, given the length of a side and any other two parts of the triangle can be solved, by which is meant all of the angles and all of the side lengths can be found if the length of a side is given and any other two parts. There are four categories to consider. If you're given the measure of two angles and one side, those come in the form angle, side, angle, or side, angle, angle. Second category, two sides and one angle opposite one of the sides are known. That's called side, side, angle. If three sides are known, side, side, side. And then the fourth category, two sides and the angle between them are known, called side, angle, side. Cases 1 and 2 above can be solved by using the law of sines. So here is the law of sines. If triangle ABC has side lengths A, B, and C, opposite angles, capitals A, B, and C respectively, then A divided by the sine of angle A is equal to B divided by the sine of angle B, which is equal to C divided by the sine of angle C. Or you could just write the reciprocal version, sine of B over B equals sine of A over A equals sine of C over C. So it doesn't take too long to prove this. The proof is based on elementary geometry and trigonometry. So I'll label the triangle ABC, and the length opposite angle A is lowercase a. The side is length lowercase a. The side opposite angle B has length lowercase b. And then the side opposite of angle C has length lowercase c. Okay, so if we construct a perpendicular from this vertex to the side AB so that we have a perpendicular line segment, and if we label the length of that as h, which stands for, it can represent the height of the rectangle, or the height of the triangle. Then the sine of angle A is equal to h divided by b. If we just focus on this right triangle on the left, the sine of angle A is h over b. But in the right triangle on the right-hand side, we can also write the sine of angle capital B is h over A. If I solve this equation for h, I get h is equal to b times the sine of angle A. And if I solve the equation on the right for angle, or for h, I get h equals lowercase a times the sine of angle B. And since h is equal to itself, we can say that b times sine of angle A is equal to a times the sine of angle B. And then if we multiply both sides by 1 over a times b, so multiply both sides by 1 over ab, 1 over lowercase a times lowercase b, I get 1 over ab times b sine of a equals 1 over ab times a sine of b. Okay, on the left, the b's cancel, and 1 over a times sine of angle a is sine of angle a over lowercase a. And on the right-hand side, the a's cancel. 1 over b times sine of angle b is sine of b over lowercase b. Through the same process, we can also show that each of those two ratios is equal to sine of angle capital C over lowercase c. So this is the law of sines. It's useful to know. Okay, we'll do some examples. So here we have side angle angle. This says solve triangle ABC, where angle A is 31 degrees, angle C is 76 degrees, and the side opposite angle C is 19. So sometimes it helps to just draw the triangle, and I'll label it A, B, and C. Angle A is known to be 31 degrees. Angle C is known to be 76 degrees. And the side opposite angle C is known to be 19. Okay, so we want to find what A is. We can determine what angle B is because the other two angles are known, and the sum of the angles has to add up to 180 degrees. So let's see, 107, so this should be 73 degrees. Okay, so there's only two things to find. This value A, which is this side BC, and also B. Okay, so we can write lowercase a over sine of 31 degrees. And then that's equal to 19 over sine of 76 degrees. And since we know angle B, we can also write lowercase b over sine of 73 degrees. Okay, well, I can solve the equation on the left for lowercase a. All I have to do is multiply both sides by the sine of 31 degrees, and I get a is equal to 19 times the sine of 31 degrees divided by the sine of 76 degrees. And then the equation on the right, I can use that to solve for lowercase b. So when we solve this for lowercase b, we can just multiply both sides by the sine of 73 degrees, and we get lowercase b equals 19 times the sine of 73 degrees divided by the sine of 76 degrees. Okay, so we solved the triangle. We found the three unknown parts. Okay, this is referred to as side angle angle because I have a side that was known adjacent to an angle that was known, and this angle is adjacent to that angle which is known, so side angle angle. Okay, the next scenario is angle side angle. Solve the triangle ABC, where angle A is 132 degrees, angle B is 28 degrees, and side C is 6.8. Okay, so angle A is 132 degrees, so I'll try to depict that a little bit. So this is my triangle ABC. And angle A is 132 degrees. B is 28 degrees. And C is 6.8. Well, with two angles known, we also know the third angle because they have to add up to 180 degrees. So that means this angle is 20 degrees. And all we have to do is find this side represented by lowercase a and the length of that side represented by lowercase b. Okay, so starting with the a, lowercase a over the sine of 132 degrees. That's equal to 6.8. That's what lowercase c is, and the sine of angle C is sine of 20 degrees. And that's equal to lowercase b divided by the sine of 28 degrees. Okay, so this is as simple as the previous example. If we solve the equation on the left, we get lowercase a is equal to 6.8 times the sine of 132 degrees divided by sine of 20 degrees. And then if we solve the equation on the right for lowercase b, we get b is equal to 6.8 times the sine of 28 degrees divided by the sine of 20 degrees. Hey, that wasn't so bad. Okay, the next page. The side-side angle case is where the lengths of two sides and the measure of an angle opposite one of the known sides are given. But the side-side angle triangle is a little more confusing, or I should say ambiguous, than the other versions. So be careful when solving a side-side angle triangle, because one of three things will happen. There may be one solution, two solutions, or no solution. Well, in the other cases, you could construct a scenario where there's no solution. But let's look at some examples of the side-side angle in the three different categories. So this one, I'm telling you right from the start that there's just one triangle that satisfies these conditions. So we have triangle ABC. Angle A is known to be 57 degrees. Side A is 62 and side B is 50. Okay, so here's the triangle ABC. A is given to be, lowercase a is given to be 62. Angle A is given to be 57 degrees. And B is given to be 50. So we need to find C, lowercase c, and we only know one of the angles, so we need to find angles B and C. Well, since lowercase b is known, we can write sine of angle A, sine of 57 degrees, divided by lowercase a, which is 62. And then that's equal to sine of B divided by 50. So we can find the size of angle B. First, we solve for sine of B if we multiply both sides by 50. So sine of B is equal to 50 times the sine of 57 degrees divided by 62. And then angle B is the inverse sine of 50 times the sine of 57 degrees divided by 62. So one thing to check when you're, if you ever have a case where there's not a solution, then something is going to go haywire somewhere. Notice that this number, 50 times the sine of 57 over 62, this one is between 0 and 1, so that's a good sign, because the range of inverse sine is from -1 to 1. So if this number is ever outside of that, then you have a case that cannot happen. Okay, but now that we know how to find the measure of angle B, then we have enough information to find angle C. So in the notation of the terms that we're using, since angle A plus angle B plus angle C has to add up to 180 degrees, we can say that angle C is 180 degrees minus 57 degrees minus inverse sine of this number. So we can simplify that a little bit. 180 minus 57 is 123 degrees, and then minus the inverse sine of 50 times sine of 57 degrees over 62. And then to find C, we can use the law of sines again. I won't write all of this down, but I'll just write down the equation lowercase c divided by sine of angle C is equal to the sine of angle A, which is 57 degrees, divided by lowercase a, which is given to be 62. So we can solve this for lowercase c. Okay, the next example is also side-side angle, but this will have no solution. So the angle A is given to be 39 degrees, lowercase a is 6, and lowercase b is 15. So we'll draw a triangle just for reference mostly. So A, B, and C are the vertexes or the angles. Angle A is 39 degrees, lowercase a is 6, and B is given to be 15. So we can write sine of B over 15 is equal to the sine of 39 degrees divided by 6. And so sine of B is equal to 15 times the sine of 39 degrees divided by 6. 15 divided by 6 is 2.5. So this is 2.5 times the sine of 39 degrees. So we have enough information to know what's going on. We know from the graph of y equals sine of x, we know that sine of 39 degrees is greater than 1/2. So sine of b, which is equal to 2.5 times sine of 39 degrees, this is going to be greater than 2.5 times 1/2, which is 1.25. But sine of b has to be between -1 and 1. So this can't happen. This cannot occur. The reason is -1 has to be less than or equal to sine of b, which has to be less than or equal to 1. So this is a case where there's no such triangle that has those those quantities. So we say that there's no solution. Yeah, a couple more examples. Okay, this one has two solutions. Side angle. Okay, so we're given angle A is 30 degrees. So ABC, angle A is given to be 30 degrees. Lowercase a is given to be 5. And B is 7. So we can start by trying to find angle B. We can write sine of B over 7 is equal to sine of 30 degrees over 5. And so sine of B is equal to 7 times, well, we might as well, since we know sine of 30, let's replace it with 1/2. 7 times 1/2 divided by 5, or 7/10. Well, sine of B equals 7/10 if you consider the graph of sine. Between 0 and pi, there are, so this is about where 7/10 is. So there are two numbers between 0 and pi where the sine of that angle is 7/10. So the inverse sine, so if we write B is equal to the inverse sine of 7/10, remember what the range of inverse sine is. The inverse sine range is from negative pi over 2 to pi over 2. So this angle is that the inverse sine gives us is this one right here. So this is the inverse sine of 7/10. So how would we find the other solution, the other triangle? So one of the triangles has this angle, and then the other one is, what should I call it? Angle B with a hat on it. It's pi minus the inverse sine of 7/10. Okay. So once you recognize it has two solutions, you just find all of the parts for each of the two triangles. But I'll try to draw a triangle just to illustrate what's going on here. So we could have one triangle like this, where this is our 30-degree angle, and this has length 5, and this is 7. And this is the bigger angle. So this angle right here is this one over here. This is the pi minus inverse sine of 7/10. And then the other triangle looks more like the one that I drew the first time, but I'll try to draw it here again. So this time, if we have the length 5 over here instead, so this is 30 degrees, this is 7. So in this picture, this angle is the inverse sine of 7/10. So it's just something to watch out for. Okay, in the next example, well, this is a toss-up. We have a side-side angle, and it either has 0 solutions, 1 solution, or 2 solutions. Okay, so angle A is in the triangle ABC, angle A is 40 degrees, side A is 11, and side B is 13. Okay, so 40 degrees. So I'll label the triangle ABC. Angle A is given to be 40 degrees. This side is 11. The side opposite angle B is 13. So we can find angle B using the law of sines. Sine of B over 13 equals sine of 40 degrees over 11. So sine of B is equal to 13 times sine of 40 degrees over 11. So 13 over 11 is bigger than 1, but we're multiplying that by a number that's just a little bit bigger than 1/2. So this is less than 1. And so it appears that this, under the given conditions, this has 2 different triangles. So this side is length 11. You can sort of see what would happen if you instead drew this side that also has length 11. So you get 2 triangles. This one is an obtuse triangle because this angle is bigger than 90. And then the bigger triangle, where angle B is smaller than 90. So it appears that it has 2 solutions, 2 different triangles that satisfy those conditions. Okay, let's look at the next topic. Which has to do with finding the area of a triangle if you're given side angle side. Okay, so if triangle ABC, or in triangle ABC, suppose angle A is given and sides lower cases B and C are also given or known. So find the area. So recall from geometry that the area of a triangle is 1/2 times the base times the height. Okay, so we will just draw a triangle for reference. I'll label it ABC. And we're given angle A, and we're given lowercase b, and we're also given C. So remember, how to find the area of a triangle. So if I construct an altitude, which is also a height, the height of this triangle can be drawn this way. I connect this vertex at angle C with a line segment that's perpendicular to the opposite side, and the length of this is called the height. And the base that I'm using is lowercase c. So the area is just 1/2 base times the height, 1/2 c times h. Well, I can use the right triangle on the left, since I know what angle A is, and I know what this length B is. I can write that the sine of angle A is equal to h divided by b, or h is equal to b times sine of the angle A. So we can write that the area of that triangle is 1/2 times c times b times sine of A, but I'll write it as 1/2 times b times c times the sine of A. Okay, so that's the area of the triangle because angle A is given and lengths B and C are also given. Okay, so in general, if you have a triangle ABC with sides lowercases a, b, and c, opposite angles capitals A, B, and C respectively, then you can have three formulas for the area of the triangle. The area is 1/2 b times c times the sine of angle A, or the area is 1/2 times A times C times the sine of angle B, or thirdly, the area is 1/2 A times B times the sine of angle C. You can see how those formulas are related, how they are similar to each of the other two. Okay, so here's an example. Two sides of a triangle are 5 inches and 8 inches, and the angle between the two sides measures 121 degrees. Find the area of the triangle. So if it helps, we can draw a triangle. So we're given an angle of 121 degrees. And this angle is between two of the sides. And the sides measure 5 and 8. So if it helps to label the triangle ABC so that you can also label the side length. And so in this one, we'll use the area formula, where the area is 1/2 times B times C times the sine of angle A. Since we have all of those quantities, we have 1/2 times 5 times 8 times the sine of 121 degrees. So we could simplify this a little bit. 1/2 times 5 times 8 is 20, so 20 times the sine of 121 degrees. But for a test question answer, this is a perfectly fine answer. Okay, another example. Two sides of a triangle are 12 feet and 6 feet. The angle between the two sides measures 76 degrees. So as long as you know that the angle is between the two sides, then you can write that the area is 1/2 times the product of the lengths given multiplied by the sine of the angle, 76 degrees. Okay, but this is where the angle is between the two given sides. So you might want to watch out for that. If you have a different scenario where the angle is not between the two sides and you want to find the area, you can use the law of sines to find the measure of the angle that's between the two sides, and then you can use the area formula. Okay, we'll look at some applications of the law of sines. Okay, so let's take a look at this one. To estimate the height of a hill, the angle of elevation is measured at 2 points that are 480 feet apart on a direct line to the base of the hill. The angle of elevation from the farther point is 32 degrees, and the angle of elevation from the closer point is 42 degrees. Find the height of the hill. Okay, so let's suppose this is the height of the hill. And then we have two different points from which angles of elevation are measured. And these 2 points differ by 480 feet. The angle of elevation from the farther point, this angle of elevation is 32 degrees. And this is in a straight line to the base of the hill. And from the second point, we have another angle of elevation. From this point to the top of the hill, this is given to be 42 degrees. And we want to use that information to determine the height of the hill. I'll label this vertical side as H, which represents the height of the hill. So how are we going to do that, I wonder? Well, we have a couple of right triangles formed. So in the green or the smaller right triangle, this angle has to be 48 degrees. So this one is 48 degrees. I'll label this side of the smaller right triangle, I'll just label it A. We might need to find what the value of A is. And in the bigger right triangle, so since this angle is 32 degrees, this big angle has to be 58 degrees. And that means that this smaller angle up here is 10 degrees. Okay, so we want to know what H is, and we probably also need to know what A is. Okay, so if we use the big right triangle, we can write that capital H, which is opposite 32 degrees, capital H, using the law of sines, capital H divided by sine of 32 degrees is equal to 480 plus A divided by the sine of 58 degrees. And then in the smaller right triangle, we can write that H divided by the sine of 42 degrees, that's the angle opposite H, is equal to A divided by sine of 48 degrees. Okay, so this equation down here came from the big right triangle using the law of sines, and this equation came from the smaller right triangle, also using the law of sines. Okay, so there's probably not enough space to do all of the work. But if we solve each of the two equations for H, so up here, solve for H, H is equal to A times the sine of 42 degrees divided by sine of 48 degrees. And if we solve this one for H, we get H is equal to the entire quantity, 480 plus A times sine of 32 degrees divided by sine of 58 degrees. Okay, so what we would do next, since we have two expressions that are each equal to H, we set them equal to each other, and then we can solve for A, and once we know what A is, we can use either of the two other equations to solve for h. So we'll set h equal to h. So a times sine of 42 degrees over sine of 48 degrees. And here we eventually want to distribute multiplication by sine of 32. So we'll write it as 480 times sine of 32 degrees plus a times sine of 32 degrees all over sine of 58 degrees. Okay, I think you know enough algebra and arithmetic that you can solve this equation for a. So I'll leave the rest of that for you to do. It's a good exercise to go through, just to think about the process involved. Okay, we'll look at one more example, another word problem. This one says a tower 90 feet tall is at the top of a hill. At 200 feet down the hill, the angle between the bottom and top of the tower is 20 degrees. Find the inclination angle of the hill. Okay, so we're at the top of a hill. We have a tower that's 90 feet tall. So this is the height of the hill. So this is the hilltop right here, and then the 90-foot tower on top of the hill. And then it says at 200 feet down the hill, so we have down the hill 200 feet. The angle between the bottom and top of the tower is 20 degrees. Okay, so the angle between the top, the bottom and the top of the tower. The bottom of the tower is the same as the hilltop. So this angle is 20 degrees. And we want to find the inclination angle of the hill. So the inclination of the angle of the hill is this angle. Let's call it theta. We want to find theta. Okay, so, well, if we label the height of the hill h, we can look at two right triangles again. So in the big right triangle, this side is 90 plus h, or h plus 90. And this angle, the big angle, is theta plus 20. No, I don't think I like that. Let's look at this smaller triangle up here. We're given one side, or actually we're given two sides, the 200-foot side and the 90-foot side. So we can find this angle up here. Let's call this angle phi. Okay, so sine of phi divided by 200 is equal to sine of 20 degrees divided by 90. So we can use this to find the angle phi. Multiply both sides by 200 and reduce it a little bit. We get 20 times sine of 20 degrees over 9. I just reduced the fraction 200 over 90 to 20 over 9. Okay, then when we know what angle phi is, we can determine what theta is afterwards. So phi is the inverse sine of 20 times the sine of 20 degrees divided by 9. And we know that theta plus 20 plus phi is 90. So that means theta is equal to 90 minus 20 minus phi, or 70 degrees minus phi. That would enable us to find this quantity. Okay, I think I'm going to move on from here. I'll think up of a better answer and I'll send it in an email a little bit later today. But for now, let's go ahead and go on to section 10.2. Okay, in Chapter 10, Section 2, we discuss the law of cosines. So for an oblique triangle, given the length of a side and any other two parts, the triangle can be solved. As we have seen, the law of sines can be used to solve angle, side angle, angle, and side angle. The law of sines cannot be used to solve side, and side, angle, side, but the law of cosines can. Okay, so here's the law of cosines. If triangle ABC has sides of length, lowercases a, b, and c, opposite of angles capitals A, B, and C, respectively, then one of the results is a squared equals b squared plus c squared minus 2bc times cosine of a. It's also true that b squared is equal to a squared plus c squared minus 2ac times cosine of b. And thirdly, c squared equals a squared plus b squared minus 2ab times cosine of c. So these might seem sort of complicated, but if you review those formulas, they each follow the same pattern, and that can help you remember what the law of cosine says. So I'll see if I can remember how to prove the law of cosines. Let's just draw a triangle ABC. So ABC, and we'll label the lengths of the sides opposite the angles, lowercase a, lowercase b, and lowercase c. So we'll construct an altitude and call it h. And for the right triangle on the left, let's label this C1 and this C2, so that the entire length of that bottom side C is equal to C1 plus C2. Then if we focus on the right triangle on the right, using the Pythagorean theorem, we can write that a squared is equal to h squared plus c2 squared. And then the right triangle on the left, using the Pythagorean theorem for that triangle, we can write that b squared is equal to h squared plus c1 squared. So if we solve each of those for h squared, up here h squared is equal to a squared minus c2 squared. And down here, h squared is equal to b squared minus c1 squared. And since they're equal to each other, we'll write a squared minus c2 squared is equal to b squared minus c1 squared. And then we'll add c2 squared to both sides. So we get a squared is equal to b squared. I'm going to put the plus c2 squared before the minus c1 squared. And then we can factor the c2 squared minus c1 squared. That's a difference of squares. So we get a squared equals b squared plus c2 plus c1 times the quantity c2 minus c1. Well, c2 plus c1 is equal to c. And note from this triangle on this right triangle on the left. So note that cosine of capital A is equal to C1 divided by B, or lowercase c1 is equal to B times cosine of A. Okay, so we're going to replace C2 plus C1 with C. We're going to replace C1 with B times cosine of A. And we're also going to replace C2, since C2 is equal to C minus C1. We're also going to replace C2 with C minus C1. So let's not do it all at once. Let's write a squared equals b squared plus c times, and then I'll replace c2 with c minus c1. So I have c minus c1 minus c1, or c minus 2c1. But 2C1 is 2B cosine of A. Okay, so we get A squared equals B squared plus C times C minus 2B cosine of A. And then lastly, we will distribute multiplication by C. So we get A squared equals B squared plus C squared, and then minus 2BC times cosine of A. Okay, that wasn't too painful. We proved one part of the law of cosines, but the other two parts can be proved in the same way. Okay, let's look at some examples where we apply the law of cosines. Okay, so we have a side angle side. Solve triangle ABC, where angle A is 52 degrees, side B is 22, and side C is 35. So as an aid, I'll draw the triangle, label it ABC. Angle A is 52 degrees, and the side opposite angle B is 22, and the side opposite angle C is 35. Okay, so this is C and this is B. So we can use the law of cosines to determine what the length of A is, lowercase a. So we write, let's just write the formula first. A squared equals B squared plus C squared minus 2 times B times C times the cosine of angle A. So we know what lowercases b and c are, and we also know what angle A is. So A squared is equal to 22 squared plus 35 squared minus 2 times 22 times 35 times the cosine of 52 degrees. Okay, then A is just the square root of all of that. Okay, and once you know what A is, okay, so we'll just assume that we now know what A is. So A is now known. By taking the square root of the right-hand side. And then we can use the law of sines to find angle B. So we use the law of cosines to help us find another side, and then to find angle B, we write sine of B over 22 is equal to the sine of A, which is 52 degrees, divided by A, which is now known. So And then once you know what the angle B is, you can find the angle C because all three angles have to add up to 180 degrees. Okay, the next example, solve the triangle. This is a side, side, side. So all three sides are given. I'll just mention a side, side, side triangle that doesn't exist. If you ever have a triangle, a side, side, side angle that doesn't exist, what would that mean? Well, if you have three sides that are given, and if the sum of two of the sides is less than the sum of, or is less than the third side, then that cannot exist. So suppose if you have A equals 3 and B equals 4 and C equals 10, then that can't exist. So why not? Well, if you draw one side of length 10, and if this side is 3 and this side is 4, well, they're just too short to meet, so that wouldn't exist. Okay, well, we don't have that situation here. So we're given three sides. Oh, let's call this A, B, and C. So A is given to be 24.6. B is given to be 16.2. C is given to be 33.5. Hey, so it's a toss-up on which angle to find first. If you want to find angle A first, then we use this formula, A squared equals B squared plus C squared minus 2BC times the cosine of A. Okay, so we have 24.6 squared equals 16.2 squared plus 33.5 squared minus 2 times 16.2 times 33.5. And I ran out of space. This is cosine of A. So there's only one unknown in that equation, so we can solve for cosine of A. So if you subtract 16.2 squared and 33.5 squared, let's write down a little bit more. So maybe without parentheses, 24.6 squared minus 16.2 squared minus 33.5 squared. Okay, that's equal to negative 2 times 16.2 maybe I should use parentheses here. 33.5 times cosine of A. And then cosine of A is what you get when you divide both sides by -2 times 16.2 times 13.5. So just a couple of steps more, and then we'll call it on this one. So cosine of A is 24.6 squared minus 16.2 squared minus 33.5 squared all over -2 times 16.2 times 33.5. And then A is the inverse cosine of that number. Then you could go through the same process to find what angle B is. And once you know what two of the angles are, you can find the third angle easily. Okay, there's an area formula in section 10.2 also. So given a triangle with sides of lengths A, B, and C, the area is the square root of S times S minus A times S minus B times S minus C, where S is equal to 1/2 times the quantity A plus B plus C. Well, we're not going to prove it. It's a pretty tedious proof. So there's the formula. We can try an example here of triangles that we know the area of. Suppose we have, let's just suppose this is a right triangle. So my drawing is not exactly to scale, but suppose the two legs are 8 and 6. So we know that the area is 1/2 base times height. So in a right triangle, you can use one of the legs as the base and the other leg as the height. So the area is 1/2 times 8 times 6, or 24 square units. So let's see if we can get this formula to work. In order to use this formula, we need to know what the length of the hypotenuse is. So let's call that C. So C squared is equal to 8 squared plus 6 squared, or 64 plus 36, which is 100. So C is equal to 10. Okay, so the value of S then, according to the formula, is 1/2 times the sum of the three sides. So 1/2 times 8 plus 6 plus 10, or 1/2 times 24, which is 12. Okay, if we assign A to be 8 and B to be 6 and C to be 10, then our area, using that formula, is the square root of S, which is 12, And then S minus A is 12 minus 8. S minus B is 12 minus 6. S minus C is 12 minus 10. So obviously more writing than is necessary, but so we get 12 times inside the square root, 12 times 4 times 6 times 2. And let's see, 12 times 4 is 48. 48 times 12 is 576. And the square root of 576 is 24. So we got the same answer. So maybe this formula is just more of a novelty. So find the area of a triangle with sides of length. A equals 12.2 inches, B equals 16 inches, and C equals 9.8 inches. Well, in a case like this, maybe this formula isn't so bad after all. So C or S is 1/2 A plus B plus C. And then the area is the square root of S times S minus A times S minus B times S minus C. Okay, so first we'll find S. So this is 1/2 times 12.2 plus 16 plus 9.8. 12.2 times, sorry, 12.2 plus 9.8 is 22. 22 plus 16 is 38. So 1/2 times 38 is 19. Did I do that right? Okay. So we'll put those numbers inside the square root. So S is 19. A is 12.2 inches. So 19 minus 12.2 is 6.8. B is 16. 19 minus 16 is 3. And C is 9.8. 19 minus 9.8 is 9.2. Okay, so that's a good enough answer for this one. Useful if you ever had to find areas of triangles where the three sides are known. You could easily program that in a Excel program or something else. Hey, here's what is said to be an application of the law of cosines. So let's give this one a try. A Coast Guard ship leaves its base at 16 knots, which are nautical miles per hour, on a course of north 82 degrees east. 3 hours later, a distress call comes in from a cargo ship that's located 180 nautical miles from base, at a bearing of north 48 degrees east. Find the distance that the Coast Guard ship is from the cargo ship. Okay, so on a map, the upper vertical is north and the rightward horizontal is east. Okay, so a Coast Guard ship leaves the base. So the origin of the intersection of the axes is the base in this picture. Okay, so the course is north 82 degrees east. So from the north, 82 degrees in the easterly direction. So this, it's 8 degrees short of 90 degrees. So it's something like this. So this angle is 82 degrees. And we're told, this is the course of the Coast Guard ship. We're told that it's traveling at 16 knots, nautical miles per hour. So in 3 hours, the Coast Guard ship will have traveled 48 knots, or I should say 48 nautical miles. So we'll label this 48 nautical miles. Okay, then there's, at that instant, 3 hours after the Coast Guard ship left, a distress call comes in from a cargo ship that is 180 nautical miles from the base at a bearing of north 48 degrees east. Okay, so 48 is a little bit more than 45 out of the north, so something like this. So this distance is 180 nautical miles. And this angle is 48 degrees. Okay, and we're supposed to find the distance that the Coast Guard ship is from the cargo ship. So this is the Coast Guard ship. How do you spell guard? G-U-A-R-D. Okay, Coast Guard ship and the cargo ship. And we want to find this distance right here. Let's just call it, call it capital A, I guess. Maybe that's a poor choice of letter, but oh well. Okay, well, in this triangle, the one with this green side, red side, and blue side, we know two of the sides, the lengths of two of the sides, and we can also determine what the measure of this angle is. This measure should be the difference in 82 degrees and 48 degrees. So that is 34 degrees. So we can find this side by using the law of cosines. So maybe I'll replace this with lowercase a because we're used to using lowercase letters for the lengths of sides of triangles. So using the law of cosines, we can write that a squared is equal to 48 squared plus 180 squared minus 2 times 48 times 180 times the cosine of this angle, 34 degrees. Okay, so with a calculator, we can find all of the numbers on the right-hand side, and so a is just the square root of that. Okay. So I ran out of notes. Let's review the law of sines, just to reiterate what we've covered. So the law of sines, so we can write sine of the angle A over lowercase a equals sine of the angle B over lowercase b equals the sine of angle C over lowercase c. Or you can write the reciprocal version. The law of cosines. Maybe you have discovered that one way to help memorize certain things is to write them down and then afterwards try to write them down from memory over and over and over and over again, and eventually you can commit it to memory. So the law of cosines, triangle ABC, sides lowercases a, b, and c. So the first one, a squared equals b squared plus c squared minus 2b times c times cosine of the angle A. Then the second equation, b squared equals a squared plus c squared minus 2ac times the cosine of angle B. And finally, c squared is equal to a squared plus b squared minus 2ab times the cosine of angle C. So since we have a few minutes, why not review some of the trigonometric formulas? So if you remember, cosine of alpha plus beta, cosine of alpha minus beta, sine of alpha plus beta, and sine of alpha minus beta. Well, I think it's pretty important to know these sum and difference formulas for sine and cosine, because a lot of the other formulas are derived from these formulas. So cosine of alpha plus beta is cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Cosine of alpha minus beta is cosine of alpha times cosine of beta plus sine of alpha times sine of beta. Sine of alpha plus beta is sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And then sine of alpha minus beta is sine of alpha times cosine of beta minus cosine of alpha times sine of beta. So make sure you absolutely know these. From these are derived other formulas like sine, the double angle formulas, like sine of 2x. Well, this is just sine of x plus x, or you can remember that sine of 2x is 2 times sine of x times cosine of x. So this one is related to that one up here. In other words, to derive this formula, we just use the sum formula for sine. Cosine of 2x. This one has 3 versions. One version is cosine of x squared minus sine of x squared. And what are the other 2? Well, the other one is, or the second one is 2 times cosine squared of x minus 1. And a third one is 1 minus 2 times sine of x squared. But this first one is directly derived from the cosine of alpha plus beta. And then to go from cosine of 2x equals cosine of x squared minus sine of x squared to this one, we replaced sine of x squared with 1 minus cosine of x squared. That's using the Pythagorean identity. That's what we did to get this one, and then to get that one from the original, we also replaced cosine of x squared with 1 minus sine of x squared. Okay, using these formulas right here, I guess we should put the tangent of 2x formula. That's 2 times tangent of x divided by 1 minus tangent of x squared. Okay, we have 2 or 3 minutes left. These formulas up here are used to write down the reduction formulas. So reduction formulas. So sine of x squared, that's equal to 1/2 times the quantity 1 minus cosine of 2x. Cosine of x squared, the reduction formula for that is 1/2 times the quantity 1 plus cosine of 2x. And then the reduction formula for tangent of x squared. We can get that if we just divide sine of x squared by cosine of x squared. And that is just 1 minus cosine of 2x in the numerator and 1 plus cosine of 2x in the denominator. Okay, we're about out of time. Tomorrow we'll cover section 10.3 and then also do the test 3 review tomorrow. And test 3 will be on Monday. But that's all for today.